So we talked about how enthalpy is a state function. And so we look at the change in the enthalpy. We can calculate a heat of reaction or a change in enthalpy for a reaction from tabulated values. These are standard enthalpies of formation. So delta H is the change in enthalpy. We can define 0 to be convenient, just like we define sea level as 0 altitude because it's convenient. And we measure changes relative to that. So for enthalpy, we define 0 as the enthalpy of a pure element in its standard state. And we measure changes relative to that point. So what is the standard state of an element? It's, for a gas, it would be the pure gas at exactly 1 atmosphere of pressure. For a liquid or a solid, it would be the pure substance in its most stable form. Some of them have different forms. At exactly 1 atmosphere of pressure, and the temperature of interest, which is usually 25 degrees Celsius. That's the ballpark number that we use as room temperature. For a substance that's dissolved in a solution, it's the substance with a concentration of exactly 1 mole per liter. So that's how we define what the standard state is. The standard enthalpy change, we add this degree sign to the delta H. Standard enthalpy change is the enthalpy change when all the reactants and products are in their standard states. And the degree sign indicates standard. Standard enthalpy of formation is the enthalpy, the change in enthalpy, when you're forming 1 mole of a pure compound from its constituent elements in their standard states. So because of how we defined all of this, for a pure element in its standard state, the standard enthalpy of formation is 0 because we chose it to be that way. So all of this information is available in tables. This is table 6.5 from chapter 6 in your book. There's also a more extensive table in one of the appendices. And then the CRC has pages and pages and pages of this sort of information. So here we're showing different bromines. So there's bromine atoms, bromine molecules, and then here's a compound containing bromine. And here we're listing the standard heat of formation in kilojoules per mole. So for this one here, bromine as a liquid, Br2, the standard heat of formation is 0 because that is the standard state for bromine. Bromine, we can tell from the periodic table with its blue symbol, is a liquid at room temperature, and it's a diatomic molecule, a diatomic element, so it's Br2. So that's its standard state. This is also bromine, the element, but this is individual atoms in the gas state, and that is not the standard state for bromine. If you wanted to make bromine atoms from bromine liquid, it would require 111.9 kilojoules per mole of energy to do that. If you're not sure if what the standard state for an element is, and you have a table like this available, you can find the one that has 0 as its heat of formation. So for carbon, there are 2 forms listed here, graphite and diamond. And the graphite is the most stable form. It's the standard form, so that has a 0 heat of formation, and the diamond is 1.88. Notice sulfur has a couple of different forms. This one is the standard state. Any questions about that table? You do not memorize these numbers. You just go look them up when you need them. So the standard enthalpy of formation, also called the standard heat of formation. For elements, the heats of formation are going to be 0 because that's like sea level, that's what we defined as 0. For most compounds, the standard heat of formation is going to be negative. because when compounds form, energy is released. So that's just like going below sea level. It's not like negative volume or something. It's just going below zero. So let's look at methane. So methane is CH4, and the standard enthalpy of formation for methane is negative 74.6 kilojoules per mole. And we can write a formation reaction equation for this. So here we have methane, and here we have the elements that are present in methane, carbon and hydrogen. These need to be listed as their most stable form in their standard states. And we always have this making 1 mole of whatever compound we're talking about. So 1 mole of CH4, so that's going to require 1 mole of carbon atoms and 2 moles of hydrogen molecules. Sometimes we'll end up needing fractional coefficients because the way this is set up, we have to have a coefficient of 1 on the product. So let's write the formation equation for carbon monoxide. So we've got carbon monoxide, CO, and we pick out the elements in there. There's carbon and there's oxygen. But these need to be in their standard states. If we're not sure what the standard state is, we can go look in the table and find the one whose heat of formation is 0. For carbon, the standard state is a solid, and it's the graphite form. For oxygen, oxygen is a diatomic element, and it's a gas at room temperature, so it's O2 gas. Now, this is not yet a balanced chemical equation, but we've got the elements in their standard states. Now we need to balance the equation without adding a coefficient to the product. We need that to be 1 mole of carbon monoxide. So the carbon's fine. We've got 1 carbon here and 1 carbon there, but I need 1 atom or 1 mole of carbon atoms, and these are O2. So I'm going to put a 1/2 coefficient here because I only want half of this. And delta H here is, you look it up in the table, it's minus 110.5 kilojoules per mole. Any questions? So we can write a formation reaction for any compound. This is not necessarily how it is actually formed, but that doesn't matter because enthalpy is a state function. Doesn't matter how you got to the top of the mountain, but the change in elevation is the same regardless. We're looking at the change in enthalpy, and so even though this may not be the method that we actually got to forming that, the change in enthalpy is the same. Okay, write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of delta H for each equation. So for sodium chloride, we're going to put sodium chloride as the product. It's a solid. And the coefficient on that has to be 1, so we don't need to leave space for a coefficient. Then we're going to look at this and identify the different elements that are present in this compound. And there's 2 of them, right? Sodium and chlorine. So we're going to write these as reactants. We've got sodium and we've got chlorine, the elements. These need to be the elements in their standard states. So for metals, are any metals diatomic elements? No, just some of the nonmetals. So you don't have to worry about its Na2 or anything like that. What state is sodium in at room temperature? It's a solid. You might say, well, I've never seen sodium. How do I know? Periodic table. This one we have on the wall, the colors of the element symbols tell us the state at room temperature. So all of the ones that are black are solids at room temperature. Blue is a liquid and red is a gas. the periodic table you get for the exam isn't color-coded, but this one's still on the wall. Yeah? What about the white one? Excellent question. Okay, so these white ones are all man-made. And so they're not naturally occurring. And some of them are so unstable that we don't even know what color they are. So we can't really say what their state is necessarily. And so we just give them that whited out symbol. They're unstable. Pardon me?
You said the white one. Is it a gas or solid?
It's just that it's man-made. So the white symbols, we're not specifying that it's a gas or a liquid or a solid. Those are all man-made elements. Pardon me? I'm sorry, this fan is really loud and I can't hear you.
No, I mean, it's like you have to be doing like compose or decompose something to make it that one.
You have to have some really high-tech equipment to make those elements. And no reactions occur with them because they're radioactive and they just disintegrate. So it's cool that we can make those elements, but we're never going to run into those in a formation reaction. Okay, so that's sodium. Chlorine. Well, chlorine, is that one of the 7 diatomic elements? Yes, it is. So we need to have Cl2 because that's what it does. And what's the state of chlorine at room temperature? It's a gas. And we can tell that from the red symbol of chlorine on the periodic table. So I've got my elements in their standard states. Now I need to balance the equation. In my product, I have 1 mole of sodium atoms, and here I have 1 mole of sodium atoms. I have 1 mole of chlorine atoms, and over here I have 2 moles of chlorine atoms. So instead of putting 2's in some places like we normally would, this has to stay 1 mole of sodium chloride. So we have to use a fraction here. And that's the heat of formation for sodium chloride. I'm sorry, that's the formation reaction. So we're also told that we need to give the standard heat of formation, and we do that by looking it up in the table. So there's the table, sodium, minus 411.2. Minus 411.2 kilojoules per mole. Let's do the next one. Lead 2 nitrate. So again, start by writing the formula for the compound as the product. So we got PbNO3 2 solid. Now we're not breaking this into ions, lead and nitrate. We're going all the way to the elements, so we're taking it completely apart. So we have 3 elements here, right? Lead, nitrogen, and oxygen. So there's lead, and there's nitrogen, and there's oxygen. Well, what physical state is lead in at room temperature? It's a solid. How about nitrogen? It's a gas. And oxygen? Also a gas. Are any of these diatomic elements? Yeah, the nitrogen and the oxygen are. So N2 and O2. Phosphorus and sulfur also form molecules as an element, but you are not required to remember those, just the 7 diatomic elements. So we've got our elements in the standard states, and now we need to balance the equation. So here there's 1 mole of lead and 1 mole of lead. So far, so good. How many moles of nitrogen? 2. And how many moles of nitrogen over here? Also 2. Great. How many moles of oxygen? 6, right? And over here I have 2. Well, that's easy enough. I can just put a 3 in front of that, and now I've got 6 moles of oxygen atoms. So that time I didn't need a fraction. The product always has a coefficient of 1. And then we need the heat of formation for this one. So standard heat of formation equals. Now, the table in your textbook chapter doesn't have this one, but it does have it in the appendix. So this is parts of table B in one of the appendices. So we can find lead nitrate is minus 451.9. kilojoules per mole. Any questions? So this table from the back of your textbook you're going to be using for lots of different things. The first column is showing standard heat of formation. The second column is a Gibbs free energy and then an entropy. And you'll be using those later in your chemistry studies. So just ignore the second and third columns for now. Oh, calculating standard heat of reaction. Standard heat of formation is the formation of a compound from its elements in their standard states. Right, so we go from elements to the compound, that's delta HF, standard, that's what we can look up in the table. If we took that compound and took it apart into the elements in their standard states, what would be the enthalpy change for that? It would be the negative, right? This is like transferring money back and forth to your checking and savings account. If I go one way, it's plus 20. If I go the other way, it's minus 20 for that particular account. You can't gain or lose energy or money just by going back and forth between two states. So if we want to look at taking the compound and decomposing it into elements in their standard states, same number, we just multiply by -1. Just change the sign. So to calculate standard heat of reaction, so this is not just a formation from elements, but we've got multiple things reacting to form something else. What we do is we imagine taking the reactants and decomposing them into their elements, because we can look up the enthalpy change for that, and then forming the products from their elements. So let's look at an illustration. No, not yet. Okay. So we can write any reaction as a sum of the formation reactions or the reverse of them. So that was Hess's law. We took those chemical equations and we tipped some of them backwards. We multiplied by 2. We did stuff so that they would add up to the final equation. Remember that? And then we did similar things to the delta H's and added them all up. So that's one way to find a heat of reaction. We can find standard heat of reaction without doing all of that mental acrobatics, I guess. Standard heat of reaction, we're taking the heats of formation for all the products, because those are being made from the elements, and we're taking the heats of reaction for the reactants, but we were taking those apart into their elements, and so we're subtracting those. The n here represents the coefficient. This funny thing here is a Greek letter sigma. It means the sum of. So this is the sum of the coefficient times the heat of formation for one product, and then you add up all of them like that. And then you subtract the sum of all the reactants. Any questions? Here's the picture. So this is the reaction. We're trying to come up with the standard heat of reaction for that reaction. What we can do is we can imagine taking methane apart into its elements. Well, oxygen's already an element, and then forming carbon dioxide and forming water from the elements. So illustrating is here. We're starting here with our reactants, methane and oxygen. We're going to decompose the methane. So that's going to become carbon and hydrogen. And that's going to require us to put energy into this reaction to tear that apart. The O2 doesn't change because that was already in its standard state. Now we imagine that we're taking these things and we're forming CO2. So forming CO2 would require a carbon and one of these oxygen molecules, and the heat of formation for CO2 is this minus 393.5. So that got us carbon dioxide, and then what's left is the hydrogen and the oxygen, forming 2 moles of water. Each mole of water, here we have the formation reaction down here. Each mole of water releases 241.8 kilojoules. We're forming 2, so we multiply by 2. So this is a little bit like that mountain analogy, right? Where we were starting down here. Oh, actually not. We're doing it backwards. Come on. This time we're going to start here. And we're going down to end up here. So the actual way that this reaction proceeds is not by coming apart into the elements and then forming carbon dioxide and then forming water. That's not how it happens. Just like the way this guy got down the mountain is probably not by flying up into the sky and then flying down, right? You can do that. You could have a helicopter, right? The helicopter has instruments that would allow you to measure how high up you went and then how high down you came, and so you could add the numbers together and figure out the change in elevation. But it's a state function. The enthalpy here to the enthalpy there, just like elevation is a state function, it doesn't matter how you get there. And so if we don't know how to measure this change directly, but we can measure it up here and here and here, then that works. Does that make sense? A little bit. So the way this would be written out to calculate this, we'd say the delta standard heat of reaction is going to equal the heats of formation for the products. Well, let's see. For the products minus the heats of formation for the reactants. And so delta ends up being final minus initial again. You take the heats of formation of the products, the final things, and you subtract the heats of formation of the initial things. We're subtracting here because for the products, we're taking them apart. And so it's the opposite of the heat of formation. So for our products, we've got carbon dioxide and we have 2 waters. So we need the heat of formation for carbon dioxide, minus 393.5, and to save space, I'm going to leave the units off. And then we have 2 water molecules. And each water molecule, or each mole of water, is going to have a heat of formation of minus 241.8. So those are the products. Everybody okay with that? And then we're going to subtract the heats of formation of the reactants. Well, here's a reactant, CH4. There's only one of them, so we need the heat of formation for methane. So that's minus 74.6. And 2 oxygens. But O2 gas is an element in its standard state. So what is its heat of formation? 0. So plus 2 times 0, okay? So we put those together, negative 393.5 plus 2 times negative 241.8 minus negative 74.6, and we get minus 802.5. So the standard heat of reaction here is minus 802.5 kilojoules. Any questions?
The water is 0 because it's not any of the bottom of the 3.
The oxygen is 0. The oxygen is 0 because it is an element in its standard state. And all of these heats of formation are from elements in their standard state. So if it's just the element in its standard state, it doesn't have a change in enthalpy. Okay? You can also take these formation equations and add them together and do things to the delta H's and come up with the same result. Right? You're going to have to turn this one in reverse so that you've got CH4 as a reactant. You're going to have to double this one because you need 2 O2s. No, wait, you don't need to do that. That one's going to be okay because you got CO2. You're going to have to double this one. And so you'll multiply that one by 2, and you'll change the sign on that one, and that's essentially what we did here. But mentally, it's much easier to not have to mess around with all of that. I showed you how that works so that you believe me that this is okay. It's not just some voodoo thing, right? It's a lot easier to just look up heats of formation for all of these and say, well, we're taking these apart, so that's negative, and we're putting these together, so those are regular, and just add them up. It's like building a Lego creation. So you've got two different things here, and you're going to take them apart into individual Lego bricks. And then you're going to put them back and you make the new things. Now that might not be how you actually do it. Maybe you only need to take a couple pieces off of one and move them to another thing. But that's what we're thinking about here. Any questions? We have an example here. Yep. Thermite reaction. Fun reaction. Powdered aluminum reacts with iron oxide. It's highly exothermic. Use standard enthalpies of formation to find the standard heat of reaction for the thermite reaction. So we're looking for standard heat of reaction. So that's going to be the heat of formation for aluminum. Now there's no coefficient in front of aluminum. So I'm going to have the heat of formation for aluminum oxide, and then 2 times the heat of formation for iron. Those are my products. And then I'm going to subtract. I need 2 times the heat of formation for aluminum. And 1 times the heat of formation for iron 3 oxide. So the heats of formation for the products minus the heats of formation for the reactants. If there are coefficients, they multiply the heats of reaction. Because if you're doing 2 moles of something, the energy cost or the energy gain is twice as much. Are any of these elements in their standard states?
Yes.
Yeah. So aluminum. Aluminum is a solid at room temperature. That is a standard state. So what's its heat of formation? It's 0. So this one is 0. And iron, And again, an element, solid, we look at the periodic table, that's the standard state, so that one's also 0. So this is also 0. So that simplifies things quite a bit. To find these delta H's, we need to go look them up in the table. So we've got Al2O3 and we've got Fe2O3. Go back to the table. Fe2O3 is minus 824.2 kilojoules per mole. And aluminum is minus 1675.7 kilojoules per mole. So then here when I'm calculating this, I'm going to put the heat of formation for aluminum, minus 1675.7. And I'm subtracting the heat of formation for the Fe2O3, which is negative 824.2. You need to be careful with all these negative signs. So minus 851.4. The heat of formation has a unit of kilojoules per mole, and then we're multiplying by a number of moles, so this ends up having just kilojoules as its unit. So the standard heat of formation for this the standard heat of reaction here is minus 851.4 kilojoules. Any questions? Let's do another one. Chemical hand warmers. Talked about these at the beginning. They produce heat when they're removed from the airtight plastic wrappers, because you open the plastic wrapper and then air can get in, and air has oxygen in it. This is the reaction that's occurring. Iron is reacting with oxygen to form Fe2O3. Calculate the standard heat of reaction, and then calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Well, the standard heat of reaction is going to be the heat of formation for the products, and that's got a 2 in front of it. So 2 times the standard heat of formation for Fe2O3. That's our only product. And then we're subtracting the heats of formation for the reactants. But what's this? Iron. Is that in its standard state as an element? Yep. So that one's 0. And how about oxygen? Also standard state. So both of those are 0, so we don't need to worry about it. So for this reaction, it's 2 times the heat of formation for iron, Fe2O3, iron oxide. So it's 2 times, and I've got that still written on the board, 824.2 kilojoules. This would be 2 moles, and this is kilojoules per mole, and so then the moles go away. Minus 824.2 times 2. Minus 1648.4 kilojoules. So, standard heat of reaction for this, minus 1648.4 kilojoules. So that's the first answer. Calculate how much heat is produced from 15 grams of iron powder. We've got a chemical equation here, and we've got a heat of reaction. So this ends up being dimensional analysis and stoichiometry. So 15.0 grams of iron and we need to convert that to moles of iron. We're thinking grams to moles to moles to grams. But energy, so we get to moles of iron, and then we can go directly to kilojoules. Because we've got the relationship between kilojoules and moles of iron. And we know the relationship between moles of iron and grams of iron, because that's the molar mass of iron. So 1 mole of iron weighs 55.85 grams. And here, kilojoules per mole, I'm going to use that standard heat of reaction, 1648.4, and that's for how many moles of iron?
4.
It's for 4 moles of iron, so I need a 4 down there. Yesterday I forgot to divide by that 4, so hopefully I can remember to do that today. Minus 110.68 kilojoules. And for significant figures, this 15.0 grams is going to limit things. So that's minus 111 kilojoules. Now, this is saying calculate how much heat is produced. Do I say that negative 111 kilojoules is produced? No. I say 111 kilojoules are produced. Because the negative and the produced mean the same thing, and so we don't want to say that over and over again. Now, how much did you pay for that Rockstar? Oh, I paid negative $3. Oh, so they gave you $3 to take it from the store? Oh no, that's not what I meant. You paid $3, right? So mastering chemistry would expect you to give an answer of positive 111 kilojoules. Is produced, words take the place of the negative sign. Any question?